Good afternoon. It's great to be here, and I'm pleased to tell you more about exoplanets today. I just want to get a show of hands for how many people were here yesterday so I can see if I should repeat my introduction, okay? So I will do a slightly different introduction. We've all had time to read the slide and how we want to change things for humanity. And it's really fascinating to consider that since the ancient Greeks, people have wondered, are there other planets out there? How common are other Earths? Are we alone? And what I really love is that whenever I talk to a group of undergrads, I often like to ask them, when did you learn about exoplanets? And often they don't remember when they learned, because when they became kind of coherent about world news and the world around them, they knew about exoplanets then, because they were discovered 15 years ago at a time when most undergrads were really too young to know about the world. And so you could say that for young people today, really young people, exoplanets are just a known quantity. And we want to take this a step further, so that at some point, children, and as they grow older, they know that Earths are out there, around bright stars, planets like our own. And so, as Phil described, the first lecture was generic about exoplanets and discovery and characterization, and today I'm going to focus on Earths. And I do have a couple of, maybe one or two slides that are similar. Here's a galaxy, photograph of a galaxy that we believe are Milky Ways like this galaxy if we could see it from the outside. And before yesterday I said like the exact thing, this is the interactive part of the lecture, how many people believe that there is another Earth out there in our galaxy? And everybody said yes. And then I asked a harder question, I said, if we were to find a planet like Earth, where would it be here? And for those who weren't here, just think about it for a minute. If you knew the answer, don't shout it out. But it was within that same red circle. That red circle represents approximately where our sun would be. And so if we want to find a planet like Earth, it would be right there. Now, in the field of exoplanets, we spend countless hours debating what is an Earth. And that actually is quite a broad definition. But one thing I want you to think carefully about and walk away with is, like Earth does not mean Earth size or Earth mass. And Venus and Earth, for example, they are approximately the same size and the same mass. Okay, but Earth has life on it, and Venus's surface is hot enough to melt lead, too hot for life. So there's a big difference between Earth mass, Earth size, and something Earth-like. And I like to call Earth-like something that has liquid water at the surface. All life on Earth needs liquid water. We want to find another planet with liquid water. And in the next lecture, in lecture 3, I'll talk more about that, and we can deviate from that as well. Now for today, I frame my talk around the questions I get asked most often. These are questions I get asked by people of all walks of life. Other professors, people on the airplane, children, journalists, just any random person, really. And it's amazing to me, they ask the same questions over and over again. Everybody has the same set of questions. And even if I actually answer the question in the talk, the questions will be asked again in the Q&A. So if you want to ask the question again, that's okay. The first question, what could aliens see looking at Earth from afar? If there are aliens out there, and I really hope there are, and they have our level of sophistication or higher, what would they be seeing on Earth? And actually, this is a really good question, because Earth is our only planet with life. And so we want to also use Earth to think, if we want to find life, what should we be looking for? So it's the same question. What would aliens see if they're there, or what would our Earth look like from far away? And what's really cool is we actually have a real movie of Earth from far away. I'm going to try to remember in this talk to distinguish between real data and then illustrations or images that are not real. And this is a real one. This is a real movie of Earth. It's taken by a spacecraft called Epoxy. Now, many of you have heard of the spacecraft Deep Impact that in July 2005 dropped a ball on a comet and observed what came out, and telescopes on Earth also observed it. Well, that telescope, Deep Impact, what was left, was actually just in space, moving around, and NASA opened up a mission of opportunity where people were able to propose to reuse the spacecraft. And I was part of the team. It's led by Mike Ahern and Drake Debbie to actually use it, reuse it again. And part of the team used it to look at stars with known exoplanets, looking for transits, and also to look back at Earth to see what Earth would look like from far away. So I'm going to start out by showing you the movie. And it's really a beautiful movie. It's a real movie of Earth. And let's see. Okay. Let's move on to the movie. It takes a minute to actually pop up. The movie's, what you need to know, especially for all the scientists here, is it's in a special color. There's 3 colors composite. But what I want you to do is look for specular reflection of bright spots on the ocean and land. And look how red the continents are in this color code, how bright the clouds are. And look how lucky we were. The moon transited. So this is what Earth looks like from far away. I'm going to show the movie one more time. And while I'm showing it, you can try to imagine what we might do with this as an exoplanet. Because remember, yesterday I said we will never spatially resolve a planet like that. So again, I was pointing out to look at how bright the clouds are, the specular reflection off the water, the red continents, and the lucky moon transit. So in the future, we won't be able to look at Earth spatially resolved. It will instead just be a point source. But it's something that will be varying in brightness with time. Because the Earth is a sphere and not just a flat disk, parts of the Earth are more heavily weighted. This is going to sound technical, but are more heavily weighted in the hemispherical integration. It just means that part that's sort of right in front of you dominates the integrated view. And actually what we'll end up getting, this is the real data, it's that image in different colors put into a time series of brightness as a function of time. The point source of brightness is a function of time. And you get these different curves here. This is just translating to longitude, but it's like one rotation of Earth. And this is the signal. It's hard to see, but this is 0.8, 0.91, 1.1, 1.2, so this is about 20% variation. And you see, as the Earth rotates and continents and clouds rotate in and out of view, contrasted with the dark ocean, you get a light curve. Now, just for a guess here, where do you think the transit is on this? When the transit, when the moon goes in front of Earth, the brightness will drop. You have two choices. So. It's either this one or this one. So you want to guess? Say left or center? Left. Yes, it is this one. And look how it's so uneven. Remember the transits from yesterday, when the planet went in front of the star, they were really quite, not box-like, but very, very uniform. And that's because as the moon is transiting, Earth is rotating, and the backdrop is a different brightness. So what happens here is that there's a student on the team, Nick Cowan, he's a postdoc now, modeled this to try to see what he could infer from Earth. And in the past, we made other models to try to see what we could infer. But essentially, you could infer a number of basic things about Earth. You could infer that it has very different brightnesses on the surface. So it has clouds or land or water. He broke it down even further and looked at the different colors and said you could claim that there were two dominating different colors, red and blue. And if you look at the albedo of all known things, although this is somewhat terracentric, you would say land and water are actually a good guess for what's there. Because water has an albedo that drops with brightness with longer wavelengths, and land actually gets brighter with longer wavelengths. In fact, you could also pull out the rotation period of Earth if you had a longer time series of data, because it seems like the weather is always changing. But in fact, there are large fixed cloud patterns due to the circulation of Earth that remain fixed. And once you had that rotation rate, you could actually look for other variation outside of the rotation rate, and you could see that there is variability on Earth. Earth is actually our most variable object in visible wavelengths in the entire solar system, and you could infer weather on the planet. And that weather is good because it's kind of the sign of liquid water. So actually you can infer a lot. So we use Earth as an exoplanet to say what specifically can we infer about Earth from far away. Now,
Sarah, can we make sure everybody can hear?
Yeah, can everybody hear? Can anyone not hear? He says he can. Very much. Now the question is, what would it take for aliens to see this kind of image? What if there are aliens out there? They're taking a movie of us. I mean, what would it take to do this? This is a really interesting question. And again, if this was a class, I would assign this as a homework problem. This actually just one of spatial resolution from far away. So to take this image, you would actually need something like 50 meter telescopes in space, all working together, and all spread out. So this would be a huge thing. I don't know if aliens would, I don't know if we would ever do this, because the whole game of exoplanet science is to try to understand what we can learn from the spatially integrated, from the average point source, and not for anything broken down like this. That would be extremely challenging. I don't know if they're doing that. I still kind of hope they are, but it would definitely be, might not be a good value for dollar spent. So the next question is, we have another real image of Earth. This is a pale blue dot, motivated by Carl Sagan and taken by the Voyager 1 spacecraft from more than 4 billion miles away. Can you see the point source? Earth, it's just less than a pixel. And it's taken by the Voyager 1 spacecraft. What I like about this is, see the red line? That red is actually from scattered light in the camera optics. But I like it because to me, it's what Earth would really look like from far away because of Earth's would eye dust. The asteroids that collide make dust which glows in the red. It reflects light preferentially in what red wavelengths, and this is actually what it would look like. So here's our Earth from far away. And in this case, what would it take the aliens, what would it take us to do? That's actually part of the later part of my talk. So to see this pale blue dot is challenging, but it's something we think we could do if we had enough time and money for it. And again, like yesterday, we're going to save most of the questions for the end of the talk, but if anything comes up that's sort of urgent or for clarification, please definitely ask it along the way. So what we really want to do with this pale blue dot is we want to measure spectra. And I do have, for the non-scientists in the audience, the cartoon version of what a spectrum is. You take the light from the star and basically break it up. And yesterday I had explained it's like looking at a rainbow. So if you see the rainbow in the sky, that's white light from the sun broken up. And if you look carefully at the rainbow, you would see some dark lines, really tiny, tiny, narrow lines where light is missing due to absorption in Earth's atmosphere. And that's essentially what we're looking for. We want to get a spectrum from another planet and look at that light spread out through the rainbow and look for the dark lines that are missing. Now on Earth, and we don't actually look at the spectrum like this on the other planet, we want to measure the intensity. How dark are these really? Is the center really dark? How does it drop off? How wide is this feature? And that ends up translating into a spectrum. So I know there's people here who work on Earth. This is what Earth's spectrum looks like to me and other people who work on exoplanets. It's Earth as an exoplanet. And what we're showing up here is reflectance. It's just normalized, so you can ignore what this axis is. And this is wavelength in microns. So this is visible wavelengths here, and this is near infrared. I've labeled water vapor, or these huge features. Here's ozone, there's ozone, oxygen, and Rayleigh scattering. Now in this case, if you don't understand graphs or know what spectrum is, what you're supposed to do is agree with me that this top plot, the curve on here, that you're supposed to agree that this is very different from a straight line. If you all agree it's different from a straight line. This is light reflected from Earth, and if there were no molecule, just divided by the sun, but if there were no molecules, it would just be a straight line. And then you can look here and see what you see on Earth, because Earth has many different molecules in its atmosphere. Too many for me to list right now. But these are the ones that would show up on a distant planet very far away with a sophisticated space telescope. So let's go through them. There's water vapor. This is a point where I switch into global warming sciences, because you know what our biggest greenhouse gas is? It's actually water vapor, not carbon dioxide. You don't usually hear about water vapor in the news because we as humans are not increasing the amount by too much. But you can see on the spot that water vapor with big features is dominating the near-infrared spectrum. So all life on Earth is liquid water. So water vapor on an exoplanet is really exciting to us, because for a small rocky planet, it would indicate a liquid water reservoir at the surface. On Earth, on rocky planets, water should be photodissociated with the hydrogen escaping to space. Okay, so if the hydrogen escapes to space, then you don't have water vapor in the atmosphere. On a giant planet, it's different because it's massive enough to retain the oxygen. And by the way, just as an aside, I don't have too many really technical graphs. This is just one. You don't have to understand this to understand the rest of the talk. What we have that we really like is oxygen. These narrow features here. Because, you know, oxygen should be in our atmosphere. And if the aliens are looking at us from far away, and they have a basic understanding of chemistry, they'll know that oxygen is something like 9 or 10 orders of magnitude more than it would be without life producing it. So we just put the atmosphere at equilibrium with the sun and with the kind of elemental abundances in our atmosphere. Actually, we wouldn't have oxygen, basically, just the teeniest amount that no one could ever detect. So oxygen is produced by plants and by photosynthetic bacteria. And it's amazing that it fills our atmosphere 20% by volume. Huge, huge amount, really. And that's actually, in a very Terra-centric view, what we're looking for. And it seems incredibly Earth-centric. But when we talk about designing space missions, like the class of terrestrial planet finder telescopes, that's what we want to do. Look how narrow the feature is. So we say we have to be able to find that feature. We can find more too, but we want to find that. And my talk tomorrow will be about biosignature gases, and I'll explain there other biosignature gases, but we like oxygen because it appears to be quite unique. I mean, there are always false positives. There's always ways to produce it that aren't by life, but there are very few of them, and they often come with another indicator. So oxygen is our favorite. Oxygen has a photochemical byproduct, ozone. Everyone's heard of the ozone hole. That shows up here. And you know, Rayleigh scattering. That's why Earth is a pale blue dot. Most people think it's because of our oceans that Earth is a pale blue dot. But in fact, the same reason our sky is blue is why Earth appears as a pale blue dot far away. So that's kind of the big picture. I'm not going to explain the bottom spectrum. That's just, by the way, just for the astronomers here, this was taken by Earth-Shine observations. This one was taken by the Mars Global Surveyor en route to Mars as a look back at Earth. So if you do work on a spacecraft, we always like it if you can look back at Earth. Often you can't, because it's traveling to Mars. Looking back at Earth is also looking at the sun, which will fry your instrument. So usually it doesn't happen. But there you go. There's what Earth looks like from far away. So to summarize this part of the talk, what would aliens see looking at Earth from afar? They'd see a pale blue dot that varies with brightness with time, varies in brightness with time. And each color varies slightly differently. And from that, you could try to infer that the planet had oceans and continents. You could get its rotation rate and see that it had weather. You could see an atmosphere that has water vapor, oxygen, ozone, and carbon dioxide. So that's what we want to do. And I just want to add at this point, because I do get asked this a lot, I really do want to believe those aliens are out there. Some of you will recognize this picture. But I don't see, personally, I see no robust, I know most of the people here will agree with this, but I don't see any evidence that aliens have this